Okay, everybody, I think that we are recording right now. So, oh, you are recording, it says. But with that, Ben, thank you so much for joining us and take it away.
Thank you. Thank you for having me. And actually, thank you for going through the introductions because in a room full of engineers, I can probably shortcut a few things. So some of these slides I'll give more attention than others. But I just want to kind of lay a little bit of a landscape of who we are and what we do before I go into the presentation. So the Northwest Council was formed in 1980. It was an act of Congress that brought together the states of Oregon, Washington, Idaho, and Montana. We're an interstate compact. Our job is basically twofold. Really, there were three main purposes that were written into the Power Act, which is the piece of legislation that formed us. One is to plan for an adequate, economic, affordable power system for the Northwest. And this came out of the era where there were a lot of forecasts that did not end up coming to fruition, and there was a lot of concern about how we planned for power. It was during the default on a bunch of nuclear projects and the Washington Public Power Supply System era that the council was formed. The other responsibility that we have is to protect and enhance the environment for fish and wildlife and mitigate for the impacts of the federal Columbia power system on the Columbia River. That is a responsibility that the director of the fish division has much more knowledge about, and so I can answer some very, very high-level questions about fish and wildlife, but not much more than that. So hopefully no one here is super interested in fish and wildlife operations. And then the last thing that is actually written into the Power Act, and the reason why I'm here and have been in many other places, is that we have a responsibility for public outreach and public involvement. Everything we do is done in open public meetings. We do a lot of modeling, we do a lot of forecasting, and we do that in such a way as to bring in a lot of people from industry and elsewhere and make sure that they're aware and able to see all the inputs, all the outputs, and really understand in a very open and broad and collaborative way what it is that we do. And so I'm going to be talking about our power planning function, where we look at the power system and we look at what we think is needed for the region. I will say, we are not making forecasts for individual utilities. If you're a Puget Sound Energy customer or Seattle City Light customer, each of those utilities has responsibilities to plan for its own system to make sure that they maintain an adequate system. They have standards that are set forth by federal organizations such as NERC and FERC that they have to meet. So this is not exactly the same thing. The council is more of a sort of collaborative, broader sort of organization where we look at what happens across the entire region. And really our statute only specifically relates us to the Bonneville Power Administration. And there's some statutory links there, and Bonneville has some particular actions that it has to take and involve the council. But overall, you can think of us kind of as almost like a think tank for the Northwest regional sort of energy issues. Let me make sure I can get through this. So this is probably not going to be surprising to anybody. I will say that this presentation is available to you, and you will see a lot of these links here that go to further material on our website. So overall, our system is dominated by hydro. Of course, beyond hydro, you see that we do have a natural gas and coal component to our system. There is the one nuclear plant in Washington by the Tri-Cities Columbia Generating Station, and a substantial amount of wind energy that is incorporated into the Northwest system. Overall, you can see here I've got the sort of average energy produced, where hydro is just under half, and you can see more sort of natural gas and coal as a component of that. This is, I think, circa 2018 or 2020. I lost that note in here somewhere. And then you can see on the nameplate, the actual installed machine capability. Of course, you have a higher percentage there of hydro and a higher percentage on renewables like wind, where the nameplate tends to be much larger than the actual energy produced. So emissions from the Pacific Northwest region have bounced around quite a bit. and this was one of our challenges when it came to the Clean Power Plan in the past. One of the things that people need to understand about our region when it comes to the electric sector is that emissions very much are impacted by the hydroelectric generation. And so you can see, generally, I'm not a big fan of using double axes, but this is one of those cases where it's nice to be able to point out two things that are very much related. The actual emissions on the left axis of the system, and you can see how those have gone up and down through time. And then the hydro generation is the green dashed line, and you can see kind of how it impacts the thermal system and other parts of our system as you see the generation come out. So the amount of emissions in our system heavily depends upon the amount of generation we get out of the hydro system, and that changes from one year to the next. So the other kind of big thing going on right now is that a lot of utilities are putting out plans where they are going to build a large number of resources. And so this was our sort of view of just the Pacific Northwest utilities. So this is only utilities kind of within our region. We did a survey looking through the different integrated resource plans that they had and said, if you added up what all the utilities are saying they're going to build, what does it look like is coming onto our system? And you can see that predominantly we see that wind and solar are going to be the main resources that utilities are planning on going forward. And it's really minimal in terms of the amount of natural gas. And probably the natural gas plan here, I would imagine, is mostly within the IRP of Northwestern in Montana. It's been a very unlikely resource to be added to our system in most of the rest of our region for sure, and actually the rest of the West as well. And that's one of the big challenges that we see going forward is a real hesitance for anyone to add in new natural gas generating resources. So our general strategy that we put out in the 2021 power plan, and we do this every 5 or 6 years, so we'll refresh again probably in 26, 27, somewhere within that time frame, is to see over the next kind of 5 or 6 years, and again, this is to see by 2027 and in broad brush strokes, about 750 to 1,000 average megawatts of energy efficiency, about 3,500 megawatts of new renewable resources, and to the extent that it's obtainable, low cost, and frequently deployable demand response. For us, that generally means something like demand voltage reductions. You're talking about electric utilities changing or having computer controls on voltage regulation that allow them to be more precise in how they meet within the regulation standards. So one of the biggest concerns that we have heard in this plan, and something that is being really gone through the entire industry, and especially, as I said, referencing the fact that a lot of people are not looking for new natural gas plants, has been about resource adequacy. And that means basically having enough resources out there to make sure that we can meet the electric demand from moment to moment. The resource adequacy in our recent sort of plan, our analysis, has two really offsetting factors going on right now. And that's causing it to be a hard sort of area for people to be pursuing. So with resource adequacy, you always kind of start from the existing system today, and then you say, okay, well, what happens as you take away resources or you retire resources? And predominantly, that's a lot of coal resources that people are anticipating are going to be retired. And then you also look at what resources are going to be added. And we have a lot of policies driving us to add more resources into the system. So we have coal resources that are retiring, but at the same time, we have policies that are putting forward really large builds of new renewable resources, predominantly wind and solar resources. So we also run a bunch of different scenarios. We say, okay, what are some of the things that could happen going forward? Because we're supposed to look into the future 20 years. And one thing that we know we might not have the right answer on is how many coal plants are going to retire throughout the West. The other thing that we don't know much about, because it's still very much an ongoing conversation, is how energy markets might change and how coordination could happen. And then, of course, there's a lot of legislation and a lot of policy that is aiming at really aggressive and rapid decarbonization. And I'll talk a lot more about that throughout this presentation. But it's just one of the biggest kind of outstanding uncertainties that we're facing right now. People saying that they're expecting the entire transportation sector to be brought onto the electric grid, or they're expecting all buildings to be electric and not natural gas. So those are the sort of things that we want to look at that really put a lot of uncertainty into how the electric system is going to have to evolve going forward. So the other thing to kind of look at as a challenge is that the cost of resources has just changed astonishingly in the last 5 or 6 years. So we do this every 5 years, like I said. This is actually our 8th power plan that we have done since the council was found. In our 7th power plan, the cheapest resource was a combined cycle gas plant. And it was, at a certain capacity factor, if it was loaded at a high enough capacity factor. And you can see here kind of in the middle of this cost data, you have a combined cycle gas turbine that's loaded at about a 60% capacity factor, meaning that, if it has a nameplate capacity of 100 megawatts, which is not the right number, but you get this sense, you would get 60 megawatts on average over the entire year loaded out of it. And under that scenario, we saw the levelized cost of energy over the last 5 or 6 years has come down substantially. So that's just, if you could run it that often, this is how much it would cost per megawatt hour you produce. It used to be well over $100. Now it's down in our anticipation here around $60. But of course, fuel is a big part of that. And I'd be lying if I didn't say that there is a bunch of uncertainty on the cost of natural gas right now because of, the geopolitical reasons around the globe really changing the gas markets and the oil markets at the moment. So there's really an astonishing amount of uncertainty in that number. This was as of the time that we did this power plan, which of course predated the Russia and Ukraine the Russia invading Ukraine sort of circumstances that are going on there that really have been driving people to increase liquefied natural gas exports from the U.S. and try to deploy things there. So that price might be a little bit higher here, but actually that kind of that further emphasizes the point that we're trying to make here, which is that if you look at the levelized cost of wind and solar, the costs have fallen to the point where they are below the cost of natural gas. And in fact, it seems likely that it was the competition from wind and solar resources that really drove the companies making gas turbines like GE to cut costs substantially to get down to where they are today. Because they used to be a lot more expensive. And no one, 5 years ago was anticipating that natural gas turbines were going to become a lot cheaper. But somehow those costs came down pretty substantially. And that might also be partially a demand dynamic going on because there's not a lot of people asking for those new plants right now. It's something that a lot of states are basically precluding, saying that they will not have new natural gas plants built within their state. So there's a lot of things that are driving towards this result. But one of the biggest shifts that we did see recently is really the cost of technologies to generate electricity has completely turned around to where there are technologies now, if you just care about the cost per megawatt hour, which is certainly not the only thing that is of concern when you're running an electric grid, but they are cheaper than the technologies that used to be the ones that we would have as kind of the basis for what the cost on the electric system would be. And in addition to all those resources, there's a huge amount of policy that is driving how the electric sector works today. So this is a very messy graph, and I'll have one that follows up that makes it a lot simpler. But what I wanted to kind of show here was that every single state, except for Wyoming, has some sort of either clean policy or legislation, RPS policy that requires a certain amount of renewable energy to be produced, or some sort of utility or community goal that is setting up a certain amount of clean energy that needs to be produced for their system. So a good example of where you have legislation is, of course, you can see Washington here, and this has, of course, the CEDAR requirements included in it, jumping up to this sort of 100% clean requirement for the utilities in 2030. I know there's a lot of finesse and detail about CEDA and that this is not perfectly representing the policy because you have the ability to do some trade-offs and get recs and things like that to meet the clean compliance. But overall, you can see that that's here and reflected. You have something like Idaho in our region where you don't have any legislative demand, right, for clean policies, but Idaho has basically three main investor-owned utilities in it. It has Idaho Power, Avista, and PacifiCorp, and all three utilities have said that they have goals to be clean by a certain date. And so when you take those into account for the Idaho service territory, you see that there's actually very aggressive goals within the state of Idaho to add clean energy into the system. So when you take this all together, and we want to be clear about what is actually driven by state law and what is driven by utility targets, like I said. And you look at the state law, and here you have the RPS requirements, and that's in that blue hashed area. That's something that we've been dealing with for a long time. We're all very aware of the requirements that states put forward for new renewable resources to be built. When you add in the clean requirements, you can see in 2030, really driven probably predominantly by California, but also by Washington and others, you have a huge jump in the amount of energy that now needs to qualify as clean, in addition to the renewable energy. So you've got a bunch of energy that must be marked as renewable and a bunch of energy that must be marked as clean. And it gets up to about 50% of the energy produced in the Western electric grid will have to be clean. And now clean is a looser requirement. So you have hydro and nuclear also qualifying for those clean sort of merits, whatever you want to call it. We don't really have clean recs yet because we haven't seen these requirements come in. But whatever it is that defines what clean is in those pieces of legislation is what's going to be meeting this. So it's not like we need to add in a bunch of things to meet that clean requirement. A bunch of things are already there in the existing system that will help you meet that requirement. But if you add the utility goals on top of it, you start to see how really aggressively we are going to be driven throughout the West to be adding in and meeting these sort of clean requirements. And that's not just about adding more generation in, it's also about how you use the existing system. When you get up to a point where you're trying to go to 80% plus of the system being clean, you're going to not dispatch the existing gas plants, or I mean, you're probably going to retire all the existing coal plants. You're not going to dispatch the existing gas plants as often because you're really trying to make sure that the 80% of the power that you are using is qualifying under these pieces of legislation or these utility targets. So policy is a huge, huge driver in the electric system going forward over the next couple of decades. So the challenge that raises is we've got a couple of things all coming together at the same time. And so we ran it through sort of our model saying, hey, what would it take to meet all of those policies along with the announced retirements that we see on the system in terms of coal, and really eliminating the use of natural gas for most purposes. Because we went around and talked to a lot of different states, and frankly, there are very few places where we expect new natural gas plants to be constructed. And so most of the places that we would expect to see natural gas, Alberta is in the Western electric grid, and it's retiring a bunch of coal plants. It's going to repower them as gas plants. I think PacifiCorp has announced some very similar sort of actions in Wyoming, where they're going to retire some coal plants and maybe repower those as gas plants. We think Wyoming is also possible if there's somebody who would look at load there, but you'd have to find the load to sync it to. Montana, I think Northwestern has been exploring gas plants. And then in Mexico, we think that there's some potential there that you might have some gas plants added as the California system and the Mexican system have had some challenges going back and forth. So we do have a little bit of natural gas in this, but it is a very, very small amount of natural gas in very select locations that we think it would be possible for it to be constructed. If you can't construct natural gas, then you have to say, what are the other technologies that we have out there? And then you have computer models fighting with what the best solution is to maintaining an adequate system with these technologies. And to be quite honest, the biggest challenge you have there is kind of the balance on batteries and how much storage you add into the system versus how much curtailment you see out of a system, where you really just overbuild renewables to meet all these requirements. And then when you don't need the energy, you just dump it. So in our projection, one of the biggest challenges we saw is that curtailment gets kind of out of hand, and the cost of storage is really not quite at the point where it's really changing this dynamic. And so the model solutions want to overbuild renewables, and they want to curtail a bunch of the output of the renewables so that for adequacy purposes, when you need the power, that you basically have overbuilt the system so that you have enough in those cases where you might not have the highest ramps on solar, or you might have a lull in the wind. Obviously, having a really large fleet is one way of making sure that you have some power coming out of those technologies. And of course, solar with storage gives you some capability to move it, but really what we see is to meet these policies, the cheapest solution is just to overbuild the system, way overbuild the system with renewables, curtail an astonishing amount of energy, and then kind of use that as the strategy for the least cost system that complies with all these policies. If you think curtailment of renewables sounds crazy and would not happen, all you have to do is go look at the California ISO website today. They have been curtailing renewables for years to very, very large extents. They've been building a lot of storage. In fact, I think now can see more than 1,000 megawatts of batteries on the California system, and they still have a massive amount of renewable curtailment on their system, and it has been growing year by year by year. We see this trend not only continuing in California, but actually really expanding to the entire West as these technologies take over. Of course, at the same time, you do have the offsetting dynamic of a substantial amount of coal coming out of the Western grid. This graphic's actually a little bit old. There's been some retirements since we started here. You can see it starts in 2019, but the overall idea here is still basically the same, that in the West, we had a fleet close to 35 gigawatts of coal that by 2030 is headed towards somewhere around 10 gigawatts. You are just going to have rapid and continued retirement of coal resources over the next decade as the system is transforming. So of course, it's not all about kind of the dynamics on the renewable side. I do want to kind of point out, and the council has been a big sort of proponent of doing our best with understanding where there are opportunities for energy efficiency, especially when it has saved a lot of energy that would have had to be produced otherwise. By our estimates, and I think our estimates are frankly conservative, we think that the region, since we started the large lift efforts on energy efficiency, has saved more than 7,200 average megawatts. And again, I think that's a conservative number. If you think of the transformational sort of nature of LED lighting and what that has done to the electric industry, you know, that's just one thing. Flat screen TVs in our homes is another good example. Plenty of things on the commercial side too. Certainly heat pumps are the latest thing that people are looking at and pursuing for energy efficiency. So finding more effective ways to use less energy and accomplish the same work has always been a big part of how our region has kept the system adequate. But some of that low cost efficiency potential is really hard to find this time around. Overall, when we looked at the kind of supply of energy efficiency, and this is especially within our first kind of 6-year timeframe, We not only have a lot of low-cost resources now that are really in competition on the renewable side with energy efficiency, we just have less of it out there. So almost 30% less available than what we had in our last power plan in this first 6-year period, and that's just the supply. And then really you have resources that have come down substantially in cost. So when you're comparing it to other resources, even the gas resources have come down substantially in cost, but the renewables for sure have created a lot of downward pressure on energy efficiency. It's hard for utilities to look at energy efficiency that cost $100 a megawatt hour when you're looking at solar power purchase agreements that are in the $35 a megawatt hour range. And so that's kind of the dynamic that has been going on lately with energy efficiency, and why we did see some downward pressure in this latest plan, because we see less supply and we see more competition. The other thing that a lot of people have asked us about is electric vehicles. Here you can see we have obviously some electric vehicles that are already captured within our forecast that are embedded in our expected loads. And this is about what we think, barring any sort of policy push or policy intervention. So we always do our forecasts kind of neutral on state policy. We assume the current policies that are passed are going to be complied with, and we don't anticipate what future policies are going to be. So in this case, we are forecasting that by 2045, the region would get somewhere around 300,000 electric vehicles onto the grid. And that's just going to be continual rising, or sorry, that's a 300,000 electric vehicles sold in 2045. So there's a rising fleet of electric vehicles that are being served by the electric grid. And this is a pretty aggressive forecast, we think. I mean, it's not one that people look at and go, you know, that it's way too low. It's not one that, you know, people who know the electric vehicle industry say that, oh, it could be a lot higher for sure. So this is kind of our baseline assumption here. So we've got it built into our loads and kind of our strategy. But of course, this is without some aggressive decarbonization changes or push. And so even with that electric vehicle forecast, and the reason I show it before I go to this slide is so that you know we're not ignoring it, right? We understand that electric vehicles are part of the future of the electric grid. We have them embedded into all of our forecasts. With selling 300,000 electric vehicles in that 2041 date for the regional footprint, we still see that the regional emissions relative to 1990 actually will be going up. And so a lot of policy out there and a lot of targets are aiming at trying to reduce emissions from 1990 levels. And we see a pretty substantial reduction in the electric sector into our future. So you can see here, in 1990, we were at about 46 million metric tons of CO2 equivalent. Now, I showed you at the beginning, every single year depends on the hydro conditions in that year. So making comparisons to one individual year is always hazardous, and yet is exactly what is done in pretty much every policy setting. So 1990 was a particular year, 2000 was a particular year, 2005 was a particular year. They each had different amounts of emissions within them. I'm making these comparisons because other policy makers have decided that these are our benchmark years. So there could have been years that were above or below 46 prior to 1990, after 1990. That's just how many million metric tons were emitted in 1990, and many targets seem to be aiming at reducing from that particular level as a benchmark. You can see our models predict that the electric sector will get down to 17 million metric tons of emissions by 2041. So in all, that's a great story for the electric sector. The challenge, of course, is that the transportation sector is going from 62 million metric tons to 109 million metric tons. And as I said, that includes our anticipated amount of electric vehicles in that last forecast. So the transportation sector's emissions are just climbing in our region because the population is climbing. And as the population climbs, the need for transportation really goes up. And you know, that was a forecast of light duty electric vehicle sales, and light duty vehicles are not the predominant emissions coming out of our transportation sector. Most of the transportation sector emissions are from heavy duty trucking. So while it's great to see all these policies and all these trends and all these renewables coming in and really reducing the emissions in the electric sector, it's not enough to meet any of the policy goals that are really set forth in the different states. So we asked ourselves, what would it take to get closer to meeting those goals? And what would it mean for the electric sector if you were to go after meeting those sorts of goals? So here you can see, again, that baseline with that 300,000 electric vehicles by 2040s. That's our orange dashed line here. We said if you could do everything other than heavy duty transportation, so you're talking about really aggressively moving the personal vehicle fleet, all the light duty vehicles over to electric vehicles, you're talking about every new building has to be electric, no new natural gas buildings. Really any other sort of lever we could have except heavy duty transportation, what would it take and what would be the impact on the electric grid? And here you can see that it is a very substantial load increase. So while we're anticipating that load will grow in our sort of regional view, when you add in all the different potential ways that you would be looking at decarbonizing by moving end uses onto the electric grid from other fuels, you see a really rapid growth in electricity. And if you carry this out, frankly, that sort of exponential curve just continues going to 2050. It's a really aggressive future where load is going, you know, up to above that 35,000 average megawatts sort of level, which is not doubling the load, but it's a lot. It's a lot of new electric load on the system. So really policy, if it continues driving down this path, is going to keep pushing more and more onto the electric grid as you're seeing some of these other resources coming in and leaving. So you've got this sort of dynamic where a lot of resources are being retired, a lot of new renewable resources are being added. At the same time, you're really seeing an explosive growth in electric load because people are, through policies, trying to push more and more things out of fossil fuel into electric end use. So while I gave you a general strategy for how much renewables we anticipated would be needed in that first kind of 7 years for our baseline and for kind of the recommendation from the council, we did do some work here and we acknowledged that you see a lot more resources are needed if this is the policy direction that the region goes down. So we recommended 3,500 megawatts of renewables. But if you really were going to aggressively go after this and you turn it over and you let the models do the calculations, you'll see it's building closer to 15,000 megawatts of renewables in our region to meet this increased load. It's also getting more energy efficiency and more demand response to try to get basically all these resources to respond to load growth based on a lot of new electric end use coming onto the grid. By 2041, those numbers get pretty substantial. Again, you see a lot more renewables, a number that seems really quite astonishing, 36,000, megawatts of renewables when that's really, I don't know. I mean, it's hard to compare to our current system. You're talking about a really massive expansion of the number of renewables within our region. A lot more energy efficiency in DR and some energy storage added in there. Now, that is without dealing with heavy duty transportation. And the reason that we did it without heavy duty transportation is, frankly, our models are not set up for the type of transformational change that would be needed if you were going to completely electrify the transportation sector. So we needed something that could kind of give a sense of what it would take And again, this is on a ramped sort of basis. So you're seeing the first, sort of first onset of it, but really it keeps going incredibly aggressively if you go past 2045 in this example. So we chose to use hydrogen. Heavy-duty vehicles, we looked at the heavy-duty vehicle miles traveled, and we used hydrogen production as kind of a proxy for how much energy would be needed. And really, we said by 2040, about 16% of the vehicle miles traveled by heavy-duty transportation would have to be served by hydrogen, and that created a need for around 4,500, almost 4,600 average megawatts of new electricity to basically through electrolysis convert water into hydrogen so that you would have enough hydrogen to drive the transportation sector. By 2045, that goes up to 42% or so. And you can see that that creates a huge, massive electric load needed to produce the hydrogen. Now, I should say we used hydrogen as a proxy, but that was a choice. It doesn't have to be hydrogen. And we do not want to say hydrogen is the technology that's going to win out on heavy-duty transportation. There's definitely a back and forth here on the heavy-duty transportation side between doing something like the hydrogen fueling or battery technology basically getting to the point where it's effective enough to carry the weight of the battery in a heavy-duty transportation for the range that you get from it. And so it could as easily be batteries as it could be hydrogen that ultimately ends up being the solution. The end result for the electric grid is no different. You still have to charge all those batteries. You still have a loss of efficiency, frankly, not just from the efficiency of basically converting the sort of electricity into something that can be stored and then converting it back to electricity, but also the loss of efficiency from carrying a very heavy battery down the road in a truck that also needs to carry other things. And so you've got some efficiency losses no matter what. You're going to have a very large impact on the electric system. You're going to have a very large electric load needed to actually be able to even make a dent into the heavy-duty transportation emissions. And this is kind of showing that as well from a little bit of a different view. So our reference case here, the red line, is again going back to the electric vehicle transportation, light-duty transportation forecast I showed you. Takes 350,000 electric vehicles being sold, really quite astonishing from today's standards. That gets you to the red line here, where you see the demand for electricity from electric vehicles. By 2045, it's like 1,500 average megawatts, which is not insubstantial in terms of a gas plant, a large gas plant being maybe 300 megawatts. Certainly the one nuclear plant being 1,000 megawatts. So you're getting a lot of cars that are going to need a fairly substantial resource in our baseline forecast, but that's not the most aggressive that you could get. So if you ask the question, well, what could you do? Forget about hydrogen, forget about heavy duty transportation, just do everything you can with the battery. Really aggressively, like pass policies that say basically you can't even buy an internal combustion engine car anymore. You can only buy electric vehicles for personal transportation. Really work it into every application that you can out there, whether that's forklifts or shipping, local trucking that's medium duty, things like that. Everything you can do with the battery gets you to the orange dashed line, where you can see you build a lot more load, maybe more towards that 5 or so gigawatts in 2045, really edging up towards 4 in 2040. I mean, that's a substantial amount of load that would need resources to serve it. But if you look at the emissions in the region, the tailpipe emissions that would be implied by that, on our current trajectory, we see emissions going up, as I showed you in that earlier graph. The reference case by 2040, transportation sector emissions continue to climb throughout the entire sort of next couple of decades. If you do everything you can with batteries, you really force that policy, everything that you could possibly push, and far more than consumer adoption here. We're talking about really aggressive policy pushing it. then you get emissions basically that can be held flat. You can keep the transportation sector to being around the same place that it is today. It's only through doing something on heavy duty transportation that you can actually start to see any reduction in the emissions from the transportation sector. And that's why it's really important to say that hydrogen or batteries, whichever one you choose, would take a lot of electricity to be able to charge, but it is the only way that we see to actually reduce the emissions from that sector so that you could even start to approach any of the goals that are out there for a reduction of emissions in the States. I want to also say we're not, so this is end use of natural gas. We're not ignoring buildings or anything like that. The transportation is by far the larger story, but we also within this case, as we built up the electric load, had all new buildings going on to electric, had existing natural gas as it basically got to end of life being moved over to electric as well. You could say from a natural gas utility perspective, there might be opportunities for that to be a production of hydrogen that's then injected into the natural gas system and burned for an end use as well. Either way, again, it's very much the same thing for us. Like the electric impact of that is very similar, whether it's producing hydrogen to put into local gas distribution, or whether it is just creating electric end use and eliminating natural gas use. You end up with an increasing load on the electric grid. And on our baseline, we see natural gas use being very much static, kind of bouncing up and down as you see kind of different weather from one year to the next, but overall being pretty static throughout the next 20 or 30 years here. And if you want to aggressively decarbonize, something has to change about that. So when we look at the total sort of energy sector, so this is not just electricity, but it's electricity, gasoline, diesel, natural gas, end use, all those different energy sectors. In 1990, we saw around 148, again, million metric tons, kind of cumulative. 2005, it went up. In our baseline for 2041, we see that going to 169 or so. Again, hydro conditions, weather would impact that. If you aggressively go after all this decarbonization, including those heavy duty vehicles that we felt like our models couldn't really get to, we could see that going down to 105 or so in 2041 on a path to being around 90. However, if you're looking for, and this is a proxy, I know Washington is looking for net neutral by 2050. Oregon has some different goals. We took this kind of aggregate in the region, saying if you took Oregon, Washington, Idaho, Montana, kind of together, let's just say you're shooting for an 80% reduction from 1990 levels. That's been a target and a point of discussion that's been floated around quite a bit. You would need to get to just under 30 million metric tons of CO2 emissions. And with our sort of partial decarbonization, pathways to decarbonization, including heavy duty transportation, you get nowhere near it. You get to about 90. But one of the things that we do that a lot of the sort of outfits out there that you might have seen decarbonization reports from don't is we only look at today's technology. We don't anticipate future technology changing substantially. We look at some sensitivity on prices and things like that, but we don't work in new technologies that might come in and radically transform the industry. And so if you want to be generous and say, okay, let's say we could continue momentum. We really kind of have some sense of what technology would be in place up to around 2035 or so, but if we could really, we're getting to a point where there might be new tools in the toolbox when you start hitting the 2040s. And those are tools that we don't know about. If you could just say, hey, let's just assume we keep that momentum, that gets you down to about 60. And again, you're still, to get to 80%, going towards 30. That's going to take some really radical technological transformation. I think this is moderate technological transformation. Technology keeps moving forward. People find new things that they can do. It's not, going from, the incandescent light to LEDs. It's more kind of moderate incremental technology improvement. If you see those sort of things, there might be some continued momentum here that we're missing. And that's mostly why I put this in, is just to note, hey, technology has done a lot of things. The technology that we will have in 2040, it's very hard for me to anticipate what that's going to be. What we can tell you is with the current set of technologies, this is a very hard path to get to the targets that are out there today. So that's hopefully a fairly good high-level synopsis. I've got some extra slides. If they come up in questions, you can certainly get to the presentation and see those extra slides. But I think right now I'd be happy to answer any questions or go back over any of this if there are any questions along those lines.
Wow, thank you, Ben. Thank you so much. That's a lot to think about, and great presentation. Let's see. I know I typed a bunch of questions into the chat, and I know a few others. Do we want to go through that, or do some people? Maybe there's some people who have questions that they wanted to ask. First one. Let me go ahead and start off with one that I had. You made the comment that the end result is no different whether you're using hydrogen for heavy duty trucking or batteries for heavy duty trucking. But my understanding is that when you make hydrogen, you're down near 30% efficiency or even less. Whereas with batteries, you're going to be, up north of 90% efficiency. So I did want to get an idea of what you were saying there. Why would there be no difference between a hydrogen economy and a battery economy? Seems a drastic difference in the heavy duty world, heavy duty trucking world.
So let me just say, I'm talking from the electric grid perspective. From the stock market perspective and certain companies' perspective, I'm sure there's a massive world of difference between those two technologies. The battery technology that you're talking about on 90%, and again, I'd have to get you down to our transportation guy who really dug into this if you wanted to get into the real weeds of the details. But my understanding when we approached this, and we went through with our advisory committee and kind of had a very big public conversation about it. Yes, absolutely, batteries are less going to be less losses. I think the electrolytic hydrogen conversions technology is also moving rapidly, and the cost is also coming down. And the biggest barrier there is the capital cost for the machines to make the hydrogen. Transportation notwithstanding being a big deal. But if you saw the capital cost for that come down really, really substantially, then yes, it might not have the same level of efficiency, but you also might have a grid that is very flooded with renewable energy, and the cost of the electricity going into it, especially if you're able to, with a very low capital cost into it, be able to kind of overbuild the system to produce hydrogen so that it produces a lot of it during hours where there's surplus and can kind of shut down when there's hours when there's not. There might be some opportunities there to kind of, if it's not necessarily increase the chemical engineering process, which I'm sure there's someone on this call who knows way more than I do about it, there might be opportunities to improve it from the cost basis or the economic basis. The battery technology, my understanding is that while it's great and efficient, you got to put it on the vehicle. And that's the big challenge there, right? It's not that you're not going to have a battery technology that can charge up the electricity and then reproduce that electricity with some level of efficiency. Like, that's pretty well-known technology. But right now, the biggest deal with batteries is the weight. And if you could bring the weight substantially down, then you have a very different proposition on batteries. So I am not a heavy duty trucking expert by any means. My kind of high level synopsis of what I understand the kind of the dynamics that are moving between those two technologies is really, if you see the weight of the batteries come down really, really substantially, then it's going to win. And it'd be the technology that people would go with, but you're still having to drag the weight. So it's not the efficiency that you would get if you did a utility scale sitting on the same spot installation of a battery, that was charging up and discharging. So your efficiency has to be derated for that sort of need to carry it.
So if I'm understanding this correctly, your transportation person is derating the efficiency of the batteries to deal with the increased weight in a heavy duty transportation scenario.
Right. If you think about it right now, you've got a certain amount of weight that you need to carry in each vehicle down it. So the vehicle miles is one way that is quantified, but it's also just about the total transportation. And so if you have something that might be able to fit in one load now, but because of weight constraints would need to be split into two loads, then it's different than just the round trip efficiency on a lithium ion battery.
Hmm. Okay. Okay. And kind of kind of a aside on that, does the transportation people, do they take into account whether there's going to be more, rail or more electrified rail, things like that, where you're not you're not carrying around the battery at all, or maybe you're carrying around a small battery to go downhill and flat, but but uphill you're going you're putting in the you got lines overhead or something.
Yeah, so we made a very and this is a broad brush assumption, so um, take it for what it is. Like we wanted to capture the dynamic you're talking about. So one, we looked at added electric load, not just for trains and rail, but also for things like boats and doing transport like ferries and things like that. So we had assumptions about how much of that. I don't generally put those in these presentations because it just gets overwhelming for people and it's not the main point. It's not the biggest problem to solve, right? But we do have additional electric load for train and for other forms of transportation. The big way that we reflect that in the actual vehicle miles in the heavy duty transportation is we kept the growth in vehicle miles to a fairly low rate of like 1% in our forecast. And if you looked at kind of the consensus without those things, it would be much higher than that. The population growth and the amount of transportation would actually see a lot more vehicle miles added in. So the way that we tried to balance that out was by having a pretty low assumption about the number of vehicle miles additional that we needed as you see the population increase in the region,
Okay.
assuming that some of that would go towards electrified transportation, whether it was rail or other forms of electrified transportation.
Interesting. Okay, great. I know there's other people who have questions. I'm very enamored by this topic, so I don't want to take it all. Let's see. Beth, you had a question. I see. Alexander, you had maybe the first question, or let's see. James Fortier, you said power scenario, not on this data. Yeah. Um, there's questions from James Fortier. You said Puget Power and Seattle City Light are not in this data. Um, I don't know if
No.
that.
What I'm saying is when we make a plan, we don't assume that we're making a plan for each individual utility. So we recommend 3,500 megawatts for the region as a whole. We don't make a recommendation to Seattle for how many renewables to buy. We don't make a recommendation to Puget. They each have their own factors that they're going to use in making those decisions. And so for us, we just kind of use a broad brush, sort of, this is what we think it should look like. But we're not down to the level of making statements or decisions or recommendations to individual utilities.
That's great. And Alexander, did you want to ask your question regarding the sharp bends in the projections?
Yeah, I mean, I think I kind of have an idea of, based on some other graphs, why it's there, but there's a kind of a reoccurring pattern in many of the projections where somewhere around 2033 and then like the 2044 to 2045 year, you'll see a sharp spike in the well,
Yes, I didn't go into it a lot,
capacity
but
and capability.
I do have it here. So let me just kind of say, one of the things that we did in this power plan is we tried to incorporate climate change and the impacts of climate change into all of our projections. And so we have a sort of historical set of temperatures, and the way that we incorporate climate change is we use the sort of GCM, the climate models that are used throughout kind of the academic industry. Those downscaled to a local level. It was work that was done in conjunction between the University of Washington and I think Oregon State University. And so when we are making forecasts, we're making it with particular weather in those forecasts. And we have particular weather that has, different GCM. So there's some variability or volatility included. But overall, the GCMs kind of should be not looked at as individual years. They should always be considered, in aggregate over larger periods of time. The way they do it in that the climate models is basically in decades. So they say don't look at an individual year in the 2020s, look at all the years and take those in aggregate to understand the weather impacts. Because we implement a very similar thing, it's kind of the same thing. Don't look at individual years in our forecasts. They could be a very hot year or a very cold year relative to what you would expect climate change to be driving. But we thought it was really important to capture that changing climate as part of our projection. And so it's incorporated here, and that's why our forecasts don't look nice and smooth like forecasts you might see normally, where you have that kind of nice little growing, bulgy sort of a cone going out from the kind of present day. Our forecasts have a lot more ups and downs to them because of this climate change implementation. That could be a whole nother hour. So I guess that's the best I can give you kind of as a starting point.
You don't know what every day is going to be, but there will be weather.
Yes.
There will be weather from day to day. Beth, or if you're on the line, do you want to ask your question, Beth Hodgson? Or I can ask it as well. I'll go ahead and ask her question. It's asked, have you done a life cycle analysis for power generation? If, for example, petroleum versus windmills, toxic metal mining for solar panels. Conservation of energy indicates that each level of processing uses energy and as such is lost in the conversion from raw materials to electricity. So she's asking about a life cycle analysis for power generation. I think what's the term for that? Embedded carbon is kind of the term that I'm more familiar with.
What we've done is not all the way there. So I'll just say, like, straight up, we didn't compare the amount of metal that goes into a wind plant compared to like the amount of metal that goes into building a natural gas plant, and the kind of inherent things in that. I know that there's a lot of concerns about rare earth metals as well. For us, again, kind of coming back to the electric sector emissions in here and the transportation emissions, we were trying to get the subset of emissions that are related and measurable kind of by the policymakers in the region. And so, we also don't have the embedded emissions for building, the heavy duty trucks or transportation or anything like that. So there's a lot of things here that might not be intrinsically there. What we did try to do was get all upstream emissions for any fuel source. So we counted the upstream methane emissions that you get from mining coal, the upstream emissions you get from natural gas, and we did our best to put those into an equivalent. Of course, any sort of methane emissions or leaking from that. And so we've done some work on trying to be more than just direct emissions at the plant. But that work's been really focused on fuel because that's a predominant source of the emissions when you're talking about most of these sectors. It's really tailpipe and out of the plant sort of emissions. Yeah. Not necessarily the emissions associated with the manufacturing.
Yeah, and I do recall a recent paper that talked about again, this was the embedded carbon, so it wasn't going into the toxicity, things, because that's kind of a different problem for sure. But I do remember the embedded carbon in a panel. It really depended on the payback period, depended on where that panel was. And I remember, like, India, the embedded carbon would be paid back in just months, like 3 or 4 months, and the embedded carbon in that not this is not the fiscal payback, but the embedded carbon would pay back in months. Whereas in Canada, it was like it was almost a whole year before the embedded carbon would pay back. Now, that doesn't have anything to do with the toxicity, although I just wonder about that.
Of course, I've seen very similar studies, and I will say we are often approached with people asking about full life cycle sort of emissions when you're doing any of this work. To our sense right now, the work needed to actually be able to do that on a sort of planning basis like what we do is just not there. Academia has some room to cover before you could really do that in a consistent way. That being said, of course, where you put any resources is going to make a big difference. And when you're putting a solar panel into a predominantly hydro-driven system, you are going to offset fewer carbon emissions. So a lot of those papers are probably just looking at sheer offset of emissions from other resources compared to an embedded emission. I'm not sure that's a totally great comparison, because I'm not sure that the alternative action is doing nothing, which is kind of the implied assumption there, right? That you're going to put in a solar panel or you're not going to do a thing. And so I think you kind of have to be careful about those sort of life cycle analyses. But yes, I've seen plenty of them myself as well.
Yeah, it is hard because we're not, how do I say it? We don't want to compare against perfection. we don't have perfection. We have solar panels and we have coal plants and a bunch of stuff in between. So pick your poison. Okay. Now Jeff Daigle had to leave, but he does have a question about whether the assumptions included possible removal of the lower Snake River dams. I think that's four dams on the Snake River. I don't know how much power those dams provide.
Yeah, none of these actually had those removed. We are in front of the council right now talking about a potential study on what that would look like. But this, particularly the power plan and the way that it's formulated, uses the existing system and any announced retirements. So because we have announced retirements for like Colstrip and some of the coal plants, we include those announced retirements. We do not have announced retirements for the lower Snake River dams, although certainly we understand there's a lot of discussion about them. So those are included as part of the system all the way through. And were they retired, it would have an impact and you would see more resources needed, a little bit before retirements, as is always the case. When you're retiring resources, usually it's not that you wait until they're gone and then start replacing them. You kind of have to make sure things are there in place ahead of time. So it, of course, would depend on the circumstances that you're looking at. In this very aggressive decarbonization case, it would be a very different answer of what would be needed to replace them than in our baseline. But that's not really what we did in the power plan. We were really looking only at those sort of announced official retirements and incremental resources of that.
Yeah. Okay. I do want to open it up. Does anybody have any questions they want to ask? I had a couple more, but I do want to open it up. Okay, while everybody's thinking about their questions, I wanted to ask about demand response. Where does demand response? I noticed it was in one of your slides, DR. How do you see that fitting in?
Yeah, so I mean, again, our general strategy calls for anything that is low cost and frequently deployable. So kind of in this way that it's not just a capacity event, but can almost be something that can help, with the system flexibility needs. And so, for us, that really came down to a couple of particular approaches that we thought were really robust through everything we looked at. DVR, demand voltage reduction, which is very similar to CVR, but you kind of have the machines in place to be able to take your feeders to a voltage level that maybe you wouldn't be comfortable with if you didn't have the computational controls that can back off the amount of generation needed to serve the electric load but keeping everything within, the ANSI standard bandwidths that are required by all the equipment that everybody has plugged in at their house. So that's something that's pretty much completely controlled by the utilities. It's something that's pretty invisible to the end users and can be a really good technology that can help not just with a sort of peaking need, but also with those flexibility needs that can be used quite often. The other thing that we saw was time of use rates, putting in time of use rates. And most people probably think of that as residential, but commercial and industrial are probably the more likely applications of those. And having sort of rates that drive people to move electricity into other times is also a good way of having something that's responsive. In the case where you're going after really aggressive decarbonization, it's frankly just a get everything you possibly can sort of scenario. It's really hard to say that any resource is off the table. So all the energy efficiency that we identified, you could pretty much assume if you're going after heavy duty transportation, you just need to get it all the demand response, really aggressive builds of renewables. You're in this explosive exponential growth scenario where you need, and in a world that is really preferencing a lot of very vastly distributed generating technologies that it's going to be very hard to build at the pace that's needed. And so I think the solution in that world is basically all of the above, get it all. And if policies start taking us down that path, I think that's the answer that people are going to go to. But in kind of the standard baseline that we were looking at, and in a lot of the circumstances that we saw with like aggressive expansion of markets or things that kind of defer the need for generation, demand response is really fighting up against some of the same dynamics that you see elsewhere, which is a high policy-driven renewable build that is going ahead of the load showing up, unless you're in this world where load starts to really go explosively exponential. And so right now, if you just kind of assume current policy holds and consumer behavior kind of holds, we're going to build a lot of resources ahead of need. And then we're going to retire coal plants and things like that. But there's still a substantial existing system out there. You have to make some pretty big assumptions, like we're going to start retiring all the natural gas plants, or we're going to have really explosive load growth before you really see a change in that dynamic because of the policies that have really brought us to where we are today.
Are there any questions? Any other questions? I have one more. There's got to be somebody who wants to ask questions. I want to ask one more question. Demand response was one. Another area that seems pretty ripe in the next, I'm going to call it the next decade, vehicle to grid. So all these heavy duty trucks are out there with their massive batteries. Most of the day they're just sitting at home doing nothing. The garbage truck comes in the morning and then it sits there plugged in. Are there opportunities there to use their batteries, use our car batteries?
Yeah, I think this kind of comes back to the same thing that I think that I said with the sort of time of use rates, right? I think everybody thinks of vehicle to grid as I plug in my driveway, and my personal car is this amazing resource that the utilities use, and the reality is school buses, garbage trucks, those sort of things, big fleets of vehicles that have these kind of repetitive patterns are probably the best resource for vehicle to grid. Where you have some flexibility, where you could actually maybe charge the batteries and discharge them. Although probably just being very selective about when and how you charge them is getting you 90% of the way there in a lot of applications. So, I think vehicle to grid is a real thing for sure. I'm a little skeptical when people start saying that every new car manufacturer that's an electric vehicle should have vehicle to grid functionality in it, because I really think the main resource that you can expect down the road are fleet vehicles. And to the same point with the heavy duty transportation, if it becomes, those sort of, if that becomes a battery application, then you would have a lot of batteries and a lot of fleets, and just kind of optimizing those would become its own real resource in a way. And it's kind of the same general idea that we had with electrolysis to create hydrogen. If you see the capital come down in such a way that you can really increase the capacity, the ability to create hydrogen, and you can do it, so that fewer and fewer hours are needed to have the machines running, you can gain a lot of efficiency there. If you could have a lot of extra trucks sitting around, for transportation that weren't being used, you could gain a lot of efficiency there potentially for the electric grid. But that would come at a really large capital cost to another sector. And the question is the capital cost of the other sector, larger than the capital cost saved on the electric side? And generally the answer is yes. Generally, when you kind of do the math on these things, you find out that the electric sector is really the place where you can be the most efficient, and the capital spent in other places is probably best to keep that capital as low as possible because it's going to be a big expense anyway. And so all the flexibility that people kind of anticipate could be available to the electric grid could at a cost. But, is that cost actually lower than the electric grid just expanding in a way that could handle those flexibility needs intrinsically?
Yeah, we've kind of electrified well, of course I'm an electrical engineer. I've electrified our house, and I'm like, gosh, if only we get the, get our car to, share its battery with the house, we could pretty much go off grid, it seems like. Okay, are there any other questions before we thank our speaker?
Been avoiding this because it's weird and almost tangential. So to what degree does if we start deploying more liquid hydrogen technologies, to what degree will we begin to implement more superconductors inside the either vehicle infrastructure or other locations that would benefit from low temperature fluids?
You're over my head there, to be quite honest.
No, it's fine. The minute someone mentions liquid hydrogen, I'm like, some weird things that liquid hydrogen does.
Yeah, no, I think stacking values, like from my perspective, on the electric side, locating those resources that are making the hydrogen in particular places could have massive value for the transmission system. So, I think there's already really big opportunities on the electric side to stack that sort of infrastructure. When you start talking, I mean, I'm totally aware that when you have big like transformers and things like that, you have to have a certain, liquids and things to cool it, and there might be some ability to stack functions there, but I have to bow out on that one. I'm just not at the level of expertise. But hydrogen as a technology, again, for the electric side, it could do a lot of things. I have now enough experience in the electric grid, and again, I think there's many people on this call who probably have more than I, that what seems really logical from the electric side is often really overruled by other needs. And so there might be really fantastic places to put hydrogen facilities that would be creating liquid hydrogen, but ultimately, like, the driving factor will be the use of it. And if the use of it is in metro areas where they want to refuel everything, then there's probably motivation to also build the hydrogen production right next to the place where it's going to be used, and that's probably the worst place for the electric grid. When the electric grid wins versus other, logic, I'll leave that to your experience, and you can make your own determination of what's going to come. But I think there's many smart things that could be done and great things from the electric side. But then when you kind of broaden your perspective and you think about all the other industries that are impacted by the decisions that you'd make for the electric side, you kind of start thinking, oh, well, no, it's probably just going to be really a little bit chaotic and a little bit ugly as we move through that process. I think that's kind of the way that you see things go. I guess my direct experience with this really is more when you look at where wind has been built in the Northwest. It wasn't built necessarily in the best place for wind, although the gorge was a great place for wind. There are really good reasons to build wind turbines there. There's also other really great wind resources in the Northwest that have no wind turbines there because there's no transmission there, right? If you didn't have the transmission, stringing the line out to a place where you had really great wind resource was just not worth the expense of it. And so you kind of have to think about all the factors that go into play when you're talking about infrastructure like that.
I was going to say, I think with that, we'll go ahead and let you go. Ben, thank you so much. Let's everybody give him a hand. At least a hand.
Good job.
Thank you really a lot. We will, gosh, if we were in person, I would have just a small token for you, a little Theo's chocolate bar, but I don't know how to get that to you right now. So, but if you're in the Seattle area, I'd love to.
Yeah.
that. So
No worries, we definitely will connect. The best way to get in touch with me if you have any follow-up questions is probably LinkedIn. You can see it right here. Here's the address. It'll be in the presentation as well. But if you have follow-up questions you weren't able to ask and you have a request for further information, please let me know. Send me a message on LinkedIn. I'll probably link you into our website where we have more of the details behind these slides. You also have a lot of links throughout this slide deck into our supporting material. You can see that like here where it says transportation model findings, which will go into more details on what we found, including often a lot of Excel workbooks and things like that, kind of getting into the weeds. So if you can't find it there, let us know, and we will try to make sure that it gets up there. So hopefully, like I said, hopefully I was able to answer all the questions, but I know that they always kind of occur to you after you go away and you're off for a few minutes and then you're like, oh, I should have asked this. So feel free to reach out to me on LinkedIn if that comes up.
well, thank you. Thank you so much. Okay, I'm going to go ahead and stop recording here. Stop recording.